This is Sean Harris, and we are going to look at the differences between symmetric and asymmetric algorithms, how they're different, what services they provide, and how they're used together. So symmetric algorithms is a different set than asymmetric algorithms, and we need to know the differences between them and the pros and cons, because each one of them has benefits and downfalls. Then we also need to understand the security services that are provided by the different algorithm types. And these security systems would be confidentiality, integrity, authentication, or non-repudiation. And we will understand then a digital envelope, which is how all of these things are used together, the symmetric and asymmetric algorithms, how they're used together. Now, before we get a little bit deeper, I am going to say, and I'm going to warn you, that I'm going to be repetitive in this presentation. And the reason I'm going to be a bit repetitive is because I've taught cryptography, I've written about it, I've talked about it at conferences, and I know that how complex cryptography usually is to individuals. So you may think that this is a little bit repetitive, but a lot of times what happens when I teach it, I go through these concepts, and then when I kind of reverse it and ask the individuals what I've said or how they work together, it's not as clear as when I walk through it the first time. So symmetric cryptography means that the sender and the receiver have the exact same key. So if I encrypt a message with my symmetric key, you need to have the same symmetric key to reverse that. So it's important to understand that symmetric keys have dual functionality, which means two instances of the keys are necessary, key 1 and key 1. So I have key 1, I encrypt a message, you have key 1, and you decrypt the message. Now, there are definitely downfalls with using symmetric keys. For example, let's say I need to get you a symmetric key. If I encrypt a message with a symmetric key, I need to get that symmetric key to you. But how do I get it to you? Do I send it through email? No, it's not protected. How do I get that symmetric key to you securely? Well, it's referred to as out of band. I've got to figure out how to get that symmetric key to you securely. And we used to use couriers, actual people that would come to an organization and have like a master symmetric key, and then they would create individual symmetric keys for all the individuals within that organization. So before I encrypt something and send the encrypted message to someone, they'd actually have to have a secure courier go over and create and give them the symmetric key. So that takes way too much time, especially today. So it's referred to as out of band. Somehow I have to get you that symmetric key securely. So this, of course, does not scale well in large organizations. If I want to communicate with 100 different people, I need to have 100 different symmetric keys. And so each one of those keys has to be delivered to each one of those individuals through out-of-band means. Now, another issue with symmetric keys is as the individual number grows, then I have to have more keys, which runs into a problem with key management. So if I just want to communicate with one person, then I have to get a symmetric key to that individual out of band, which isn't that difficult considering if I want to communicate with 100 people. If I want to communicate with 100 people, then I have to have an instance of the key for each one of those individuals. So if I have to communicate with 100 people, I would have to have key 1, key 2, key 3, etc. If I communicate with one person, then it's just key 1, and the receiver has key 1 also. So there's actually a simplistic formula that we need to know to figure out how many keys are necessary for the individuals to communicate. So we see that the mathematical function is n times n minus 1 divided by 2. So if we have 3 users, 3 is n, so that's 3 times 2 divided by 2. 3 times 2 is 6 divided by 2, so that's 3 keys. So that's not as big of a deal compared to if we have 1,000 people we need to communicate with, which is close to 500,000 keys. Now you do need to know this formula. You'll be asked to potentially carry out a simplistic formula using this, a simplistic example. And you also need to understand the concepts of the downfalls with symmetric keys, which we talked about, that one is out of band. We have to get that key securely to the destination. And another one is a scalability with key distribution. It's very difficult as the number of keys increase. So here we just see the concept again, is that we have the formula n times n minus 1 divided by 2. And as I said, I'm going to be repetitive on some of these concepts because you need to have a foundation. You need to understand the foundations of the symmetric and asymmetric algorithms before we can show how they're used together and their deficiencies. So, weaknesses with symmetric algorithms. Key distribution. How do we get that key to the other end securely? Scalability. As we need more and more people, as we need more and more unique keys, the key management gets out of control. And one thing we didn't talk about is the limited security provided by symmetric algorithms. Symmetric algorithms can only provide confidentiality. They cannot provide true authentication or non-repudiation. So authentication is that a message came from a specific individual. So if you need to know that a message came from me specifically, we cannot use symmetric algorithm. And why is that? That's because you and I share the exact same key. You do not know that something came from me specifically, or it can't be proved that a message came from me specifically. Let's say I did encrypt a message and send it over to you, and you could decrypt it. Now, if somebody comes to me and says, Sean, why did you encrypt and send that message? I could say, well, you can't prove that it was me. There could be two people because two people have an instance of the same key. So through symmetric algorithms and keys, we cannot provide true authentication. Now, non-repudiation is close in that I can't deny sending a message. Non-repudiation means the sender cannot deny sending a message. But symmetric algorithms do not provide this type of security or this type of service because it's the same idea. Non-repudiation means that the sender cannot deny sending a message. Well, if we're using symmetric algorithm, if we're using symmetric keys, I can deny it. When somebody asks me, why did you send this message? I could say, look, you don't know it came from me, because somebody else has that key also. Now, symmetric keys and algorithms can provide confidentiality. If I encrypt a message, only you should be able to decrypt it, because we should just have two instances of the same key. Now, sometimes organizations will have several instances. So, for example, if I needed to talk to 10 people, I should have at least 10 different keys. If we all use the same key, so if 10 different people have exactly the same key, there's not confidentiality, because if I send a message to Sue, Bob can decrypt it because he has the exact same key. So we do need to understand the weaknesses or the downfalls with symmetric algorithms, which is key distribution, scalability, and they only provide confidentiality. So for the CISSP exam, you will need to know examples of symmetric algorithms, and we're not going to go through them in this presentation, but for the exam, you do need to know specifics about these algorithms, the key sizes they use, the number of blocks they actually go through, and you need to know which algorithms are symmetric versus asymmetric. Now we're going to jump into asymmetric algorithms, and asymmetric cryptography has another name, which is public key cryptography. Public key cryptography. So asymmetric means two different keys where symmetric means the same key, asymmetric means two different keys. And so the two different keys are public and private. As the name suggests, public keys can be used in the public. Anybody can get a hold of the public key and there's no security issues. The private key should only be used by one individual. So if I have a private key, it should only be used by me and no one else. So a private key cannot decrypt any data that has been encrypted by a private key. So a private key, if I encrypt something with a private key, it cannot be decrypted by a private key. Because if you encrypt something with a private key, it could only be decrypted with the associated public key. So if I have a private key and you have my public key, if I encrypt something with my private key, you could decrypt it with my public key. Now it has to be my public key. It can't be anybody else's, because the private and public key are generated at the same time and they're mathematically similar. That's how the decryption and encryption happens back and forth. So let's look over this. This is the main concepts that we're going to go through in this presentation. What key decrypts what key encrypts what, and what services are actually provided when these functions take place. So data encrypted with a public key is decrypted with a private key. Data encrypted with a private key is decrypted with a public key. And data encrypted with a public key cannot be decrypted with that public key. Now, again, what you should do is ask yourself when we're done with this presentation, and we're going to go through these questions, but you need to ask yourself, if I encrypt something with my private key, who can decrypt it? If I encrypt something with my private key, who can decrypt it? If I encrypt something with your public key, who could decrypt it? Now we're going to go through these because it's usually a bit confusing for people. So before we get to those security services, let's look at some reasons that we would use asymmetric cryptography. Now it's easily scaled. Now what do we mean by that? It's scalable. Well, with symmetric keys, we needed to have 2 instances of every key. So if I had 100 people to talk to, those are a lot of keys I need to keep track of. In asymmetric key, I only need to have my pair, which is my private and public key, and you need to have my public key. So I don't have a bunch of instances of the same keys that I need to keep track of, because 100 people can have my one public key, and they encrypt information with my public key, and then I could decrypt it. So that's what scalability means. You don't have as many keys that you have to keep track of. And it doesn't require out-of-band key delivery. Why would that be? Why would you not need out-of-band key delivery in asymmetric? Well, it's the same idea in that if I have a public key, anybody can have that public key. So I don't have to worry about securely getting it to you. It's public in nature, so anybody can have it. Now I need to keep a hold of my private key, but there's only one of those. So let's look through this. Tom, Jen, and Brad can all have my public key. Well, they all can have Dave's public key here. So Tom, Jen, and Brad can all have Dave's public key. And Dave is the one who has his private key. So that's where we get into scalability issues, which is controllable in asymmetric algorithms. In symmetric algorithm, Dave has to have a copy of each one of these people's symmetric keys. So if Dave wants to communicate through symmetric cryptography, he has to have a copy of Tom, Jen, and Brad's key. So let's go ahead and step through this. The sender, this is symmetric keys. The sender We have the same key, so how do I keep it secret? How do I send the key securely? So we're going to use symmetric and asymmetric together. We're going to use symmetric and asymmetric cryptography together. Let's think about how that would work. I have a symmetric key that I need to get to you securely. Do I send it through email? No. If I send it through email, that symmetric key is not protected. I would have to get it to you out of band. Well, let's look at a better way than out of band communication. If I have that symmetric key and I need to get it to you securely, I'm going to encrypt it with your public key. So if I have a symmetric key that I need to get to you, I encrypt it with your public key. And why do I do that? Because only you have the associated private key. If I encrypt something with your public key, only you have the private key that decrypts it. So if I encrypt an instance of a symmetric key and send it to you, encrypt it with your public key, only you can get it. That's confidentiality. And just to review, remember we're going to go over these concepts a few times. The scalability issue with symmetric key is using this formula, n times n minus 1 over 2. And so we see if we have 1,000 users, how many keys we have to keep track of. And if it's just symmetric, remember we have to get all of these to their destination securely. What about asymmetric? How many keys do we actually need? So here we show that asymmetric cryptography uses key pairs. So remember, a pair is 2. So if we have n number of key pairs, we have if we have n number of users, we have n number of key pairs. So if we have 1,000 users, we just have 1,000 key pairs. Each person has to have their own key pair. Now, what if we have 1,000 users? How many keys? Not key pairs, but how many keys do we need? That's different. Make sure that you don't get tripped up by that. Key pairs mean that individuals have their own pair. You have your public and private key. I have my public and private key. I can send you my public key. You could send me your public key. Each of us will use each other's public key to encrypt data. So I will have your public key. I'll encrypt data with that, send it to you, and only you could decrypt it because you have the associated private key. Well, it seems like asymmetric solves our problems. We don't have to go through out-of-band communication because the public key could be sent to any destination securely. We don't have the scalability issue because we only each person has 2 keys they have to keep track of, their public and private key. So what's some problems here? Well, asymmetric uses much more complex mathematics compared to symmetric algorithms. So since asymmetric algorithms have more complex mathematical functions, they're slower in nature. So symmetric has easier and less complex math, so they are faster than asymmetric. And since asymmetric is so slow, we only use them to encrypt a small amount of data. So the symmetric keys are used to encrypt bulk data. Bulk means a lot. Asymmetric keys are used to only encrypt a small amount of data. So since each of these algorithm types have their own pros and cons, we will get to how they're used together. Okay, let's go ahead and compare these. How many keys do we need on symmetric versus asymmetric? Well, symmetric is shared between 2 individuals. Asymmetric, we only have public and private keys. Key exchange, symmetric we have to do out of band. Asymmetric, we could send that public key safely to the distribution or the destination. Speed, remember, symmetric has less complex mathematics, so symmetric is faster. Asymmetric is slower because of the more complex mathematics and logic functions. Now let's go ahead and jump down to the security services provided. Symmetric only provides confidentiality. Remember that it cannot provide authentication and non-repudiation. And why is that? Why can't symmetric provide authentication or non-repudiation? With symmetric keys, we cannot prove that one person sent something. So again, if I encrypt something with a symmetric key and I send it to you, you have to have the exact same symmetric key. So somebody cannot prove through cryptography that I sent a message, since there's two instances of the same key. With asymmetric, if I encrypt something with my private key, I'm the only one who's supposed to have access to my private key. So that's how it's authentication and non-repudiation. Remember, non-repudiation means a sender cannot deny sending something. Okay, so we saw a list of symmetric algorithms you need to know. This is a small list of asymmetric algorithms you need to know. And again, we're not going to go into the specifics on this presentation, but you do need to know them, the actual specifics for the exam. Okay. If I encrypt data with your public key, who could decrypt it? If I encrypt data with your public key, you're the only one who could decrypt it because you have the associated private key. If I encrypt data with my private key, who could decrypt it? So if I encrypt data with my private key, anybody with my public key can decrypt it. Remember, several people can have my public key. If you encrypt data with my private key, who could decrypt it? Well, if it's encrypted with my public key, then only I can decrypt it because I have the associated private key. If I encrypt data with your private key, who could decrypt it? So if I encrypt data with your private key, who can decrypt that? Well, that's a trick question because I should not have your private key. Only you should have a copy of your private key. Okay, so let's look at what services are provided. And this means confidentiality, authentication or authentication or non-repudiation. So we need to know what the services are provided for each algorithm type. So if I encrypt data with your public key, what service does that provide? So if I have your public key, who can decrypt that? Only you, because you should be the only one who has your private key. So if I encrypt data with your public key and you're the only one who could decrypt it, that would be confidentiality. If I encrypt data with my private key, who could decrypt that? Anybody with my public key. So if I encrypt data with my private key, anybody can decrypt it who has my public key. And why in the world would I do that? Why would I encrypt something if anybody with my public key can decrypt it? Well, that's how authentication, authorization, non-repudiation is provided. So if you need to know that it came from me, this message came from me, then I'll encrypt data with my private key to prove it came from me specifically. If you encrypt data with my public key, what does that provide? So if you encrypt data with my public key, that's basically the same as number one. I'm the only one who could decrypt it because I have the associated private key. So that's confidentiality. Since I'm the only one who could decrypt it, that's confidential between you and I. Okay, so let's take some steps to understand how they're used together. Remember that symmetric algorithms are less complex mathematically than asymmetric. So symmetric algorithms are less complex, thus they're quicker. They're faster than symmetric algorithms. Because they're faster, we use them to encrypt more data. We use symmetric algorithms to encrypt bulk data. Asymmetric algorithms can only encrypt a small amount of data. So the symmetric key is used to actually encrypt the message. The message itself is going to have a lot of data. We can't use asymmetric algorithms on a whole message because it will take too long. So what does the asymmetric key then encrypt? It encrypts a small amount of data. It encrypts an actual key. So I will have your public key, and I will use that public key to encrypt a symmetric key. So let's look at these steps. I write you a message. That message needs to be secure. I encrypt the message with a symmetric key, and then I need to get that symmetric key to you securely. So I encrypt that symmetric key with your public key. I send those two together. I send the encrypted symmetric key and the encrypted message to you. So you have a message that's been encrypted with a symmetric key. That symmetric key is encrypted with your public key. Since you're the only one who has your private key, you use your private key to decrypt and extract that symmetric key. That symmetric key is then extracted to use to decrypt my message. So let's walk through this because it is a little bit complex. There's a message. Why are we not going to encrypt this message with an asymmetric key? Because asymmetric algorithms take too long. So we have a message, we're going to encrypt it with a symmetric key. Now if we need to get that symmetric key to the destination, how do we secure it? We encrypt that symmetric key with the receiver's public key. So what does the receiver receive? The symmetric key is encrypted with their public key, and that message is encrypted with the symmetric key. The symmetric key will be decrypted by the receiver's private key, and then the message will be decrypted with that symmetric key that was just extracted. So remember, an encrypted message is sent to the receiver. That message is encrypted with a symmetric key. The symmetric key arrives encrypted with the receiver's public key. The receiver needs to be able to decrypt and extract that symmetric key, so they use their private key. So this is what's referred to as a digital envelope. An envelope means that the message is encrypted. Now, is it encrypted with an asymmetric key? No, we don't encrypt messages with asymmetric keys because they take too long. So in a digital envelope, the message is encrypted with a symmetric key. Symmetric keys encrypt bulk data. We need to get that symmetric key to the destination securely. So what do we encrypt that symmetric key with? That's the destination's public key. So the symmetric key is encrypted with the receiver's public key. This symmetric key that's encrypted and the symmetric key that's encrypted with the receiver's public key and the message that's encrypted with that symmetric key goes to the destination. That's what's referred to as a digital envelope. The receiver will take their private key and decrypt and extract the symmetric key. The symmetric key is then used to decrypt the message. So this is a lot to take in if this is new to you. If you know cryptography to any degree, these are the basics. These are foundations that you need to understand. So how do we ensure that let's say we need confidentiality. How do we ensure that's in place? Well, if I need to get something to you, let's say a symmetric key, if I need to get that to you securely, do I encrypt that with my private key? No, because anybody with my public key can decrypt and extract that symmetric key. that symmetric key, I encrypt that with your public key because you're the only one who has the private key to decrypt it. So if we need confidentiality, we take the receiver's public key and encrypt it, and the receiver has the private key to decrypt and extract that symmetric key. What if we need authenticity, meaning we need to know who sent that message? Well, the sender needs to use their private key. So if we need authenticity, meaning we need to know who actually sent a message. If you receive a message from me and you absolutely need to know who it is, then I have to use my private key. If I use my private key, that means it came from me. The message came from me, and you know who it came from because I'm the only one who's supposed to have my private key. Non-repudiation is similar in that if I use my private key, I can't deny sending the message. Since I'm responsible for protecting my private key, and I'm the only one who's supposed to have it, if I use it on a message, then I can't deny using it. Okay, so again, I was a bit repetitive, but I do find that a lot of people have problems with understanding symmetric algorithms versus asymmetric algorithms, but really what gets more complex is how they're used together. So you do need to know the types of symmetric algorithms and their downfalls. Asymmetric algorithms, you need to know examples of those, their downfalls, and their pros and cons, and what security services each algorithm type provides. So we covered confidentiality, authenticity, and non-repudiation. So in the next lesson, we're going to go through how hashing and digital signatures are used. Thank you so much for your time.